All right, so this question says that a body of mass of 12 kilograms is dropped vertically from rest from a height of 80 meters. Ignoring any air resistance, we're going to draw the draw the motion graphs that represent potential energy and kinetic energy based on the distance fallen. So if we have our object here, right, and we have a height of 80 meters from here to here, and then here our object here, and it's just going to fall straight down to that position, right? So this will be our h equals 0 down at the bottom, and what we would say is that the energy potential due to gravity is all here. Its kinetic energy at initially would be 0, and down here my gravitational potential energy would be 0, and my kinetic energy would have all of it. So how are we going to draw that based on our graphs? All right, so we're going to draw two graphs here. One of them is the potential energy, one of them is the kinetic energy. Oopsie. And those are based on my height, right, or the distance that it's fallen, okay? Now, initially, if we look at gravitational potential energy is mgh. And so if we look at this in terms of y equals mx plus b, here's my y, here's my x, and then this is mx plus b, right? So in terms of this, my gravity times my mass is going to be my slope. So I should have a constant slope here, and I'm going to create a line that just looks like this, right? Where this is my starting potential energy, and at the very bottom, I have 0. If we do the same thing for kinetic energy, we have 1/2 mv squared. But we also need to understand that my total energy is going to equal my potential energy plus my kinetic, right? And so my graph over here is going to look just the mere opposite, because we need like this value plus this value here. This value here would need to add up to my total. So if my potential energy is being lost at a constant rate based on my height, my kinetic energy is being gained at a constant rate based on my height. All right, now the second part of the question says, do the same thing in respect to time. And now my time graphs are going to look a little bit different. Okay, so for time, potential energy based on time, and kinetic energy based on time. Right? This graph is going to take more of a shape that looks like this, okay? Because as I fall, I'm going to be going faster and faster and faster and faster. So I'm going to be covering more ground each moment. So I'm going to be losing potential energy even faster. Right? And my kinetic energy then would look something like this. Because I'm moving faster and faster and faster, my kinetic energy is going to increase more and more and more, because I'm going faster and faster each moment. Right? Last part then, it says describe qualitatively the effect of a constant resistance force on each of the 4 graphs you drew. And so I would interpret that based on air resistance, which if we had air resistance, describe qualitatively the effect of a constant resistance force. Yeah. So as something is falling, if there is some constant force due to the air resisting it, right, that's going to not really change this graph, because this graph is all based on height. So it doesn't matter how long it takes me to get there, it just matters where it is. So I would have a graph that looks something like this, whereas these graphs will probably change a little bit, because I am eventually I'm going to reach terminal velocity. Terminal velocity meaning I have a constant velocity downward. So I would expect my graph to look something like this and eventually get to a constant slope here. And same thing here. I would have it eventually get to a point where we have that constant slope there. So that's how I would expect the graphs to change, because during that part, then I'm not speeding up or slowing down. I'm just maintaining a constant velocity. And so while my energy, with this one specifically, if I'm not increasing that, right, this would actually become flat because my kinetic energy is not being increased. However, my potential energy would still decrease. Yeah, so let's redraw this. Let's rethink this. If I get to a point where I have a constant velocity, my kinetic energy will no longer be increasing. So I would expect it to look something like this, where my kinetic energy doesn't change. However, my gravitational potential energy would continue to go down. And essentially, that's because I'm going to be losing some energy due to the work that's done to the air. So really, this graph would stay the same. I would keep this graph then. I would make it a little bit flatter, right? And again, there's going to be a point where it doesn't have as much kinetic energy, so that's would be a better representation there. So hey, sometimes when you think through it, at first it doesn't make sense, but then here we're not going to be speeding up as much, so I'm not going to be gaining as much kinetic energy. However, my potential energy here would look identical. All right.